Now we have finished the example. Let us go to the quadrature separate spectrum receiver. And in this time, I'm going to talk rapidly about the system. Now we have a quadrature separate spectrum modulator. Now, how it works? Look, please. At the beginning, we have digital data, okay, D of T, serial to parallel converter. So serial to parallel will split the data into upper and lower panel. Upper panel will be considered as what? As in phase panel, and the other will be quadrature phase. As you know, the sine and cosine, there is 90-degree between sine and cosine signal. This is the edge of T for the in phase panel, and this one for the quadrature phase. And finally, the upper panel is multiplied by cosine omega ct, while the lower panel will multiplied by sine omega ct, and combined together to determine the quadrature separate spectrum signal. Now, what will be the benefit of the quadrature separate spectrum modulator? As you can see, we have the same frequency, which is omega c, but we have different phases. So the data rate here is doubled by using two phases. What about the receiver, quadrature receiver, separate spectrum? Again, first of all, we have to down convert the frequency by multiplying by cosine omega ct and sine omega ct, filter and in phase code and quadrature code, and here we have the matched filter, I mean integration, and then thresholder, and finally we have parallel to serial to get the original data. Well, by now we have finished the first kind of the separate spectrum system, which is the direct sequence separate spectrum. You can note that the operations of the direct sequence separate spectrum is done where? In the time domain. Okay, in the time domain, we have performed the operations of the direct sequence separate spectrum. Now we have another system which is called frequency hopping separate spectrum system. Frequency hopping separate spectrum system, we are going to perform the following diagram. Look at this diagram really to understand what's going on. Now, these slots, okay, represents what? Represents channel, okay, channel number 1, 2, 3, 4, 5, 6, 7, 8. Now here we have 8 channels. Now, just as this represents what? The total bandwidth. Look, this represents what? Represents the frequency axis, and each block represents a channel. So this will be the channel number 1, 2, 3, 4, 5, up to channel number 8. This axis will be what? Will be the time axis. I mean, this will be the time slot 0. Then time is advanced step by step up to getting this point. The other dimension, the third dimension, will be what? Will be the power. Now you can imagine that the carrier location at the first time slot, for example, at channel 8, then when time is advances, for example, the carrier will appear at channel number 7, then to the channel number 2, 5, 3, 2, 7, and so on. Of course, the location of the carrier becomes what? Becomes random, and is controlled by what? By a code generated at the transmitter. This code is called frequency hopping code generator. Now, in the direct sequence separate spectrum, if you are going to recover the original signal, we need what? We need the chip code in order to what? To disparate the information signal and recover the M of T. In the frequency hopping separate spectrum system, the location of carrier will be determined according to what? According to the chip code C of T. Well, Now, going back to the frequency hopping separate spectrum system. Now, based on this idea, I mean that 3D diagram, I mean in the frequency domain, and the carrier will jumps, okay, will jumps up among the available channels. Well, two kinds of frequency hopping system we have: fast frequency hopping and slow frequency hopping system. Fast frequency hopping, where complete or a fraction of data symbol is transmitted within the duration between carrier hops. Okay, what does it mean? It means that the jumping or hopping frequency is greater than the bit rate. On the other hand, in a slow frequency hopping system, more than one symbol is transmitted in the what? In the time between two hop frequency hops. In other words, if the time of hop is less than the time of single B, this will be what? Fast hopping. If time of hop is greater than the time of B, at that time we have what? We have slow frequency hopping. Now let's go to the what? To the transmitter of the frequency hopping system. Transmitter for the frequency hopping system is as follows. Look, we have the signal m of t multiplied by the main carrier. Then it will be multiplied by the signal generated from the synthesizer. Of course, to understand this diagram in a good way, let us explain what's going on in the whiteboard. The whiteboard, I'm going to explain the operation of this circuit. Look, please. At the beginning, we have m of t, and multiplied by main carrier. Okay, this will be main carrier. Then it will be multiplied by what? Look, here we have f edge code. Okay, and another block, which is what? Which is the synthesizer. And here we have a clock. Of course, synthesizer will convert a code into frequency. Now, let us explain the values on the diagram. At this point, exactly, look at this point, we have m of t cosine omega ct. Okay, m of t cosine omega ct. Well, now we said that when I have explained the operation of the frequency hopping, we said that we have channels and the carrier will jumps among what? The channels. So, and the location of the carrier will be determined by what? By the code. Now, to understand this diagram successfully, now assume that we have 8 channels. Okay, if we have 8 channels, how many number of bit code we need? 3 bits, really. Look, 2 to power 3 will be what? Will be 8 cases. Okay, will be 8 cases or 8 states. Now, starting from 3 zeros and ending by what? 3 ones. This is the code. Now, when, for example, okay, when the code is 100, at that time the synthesizer will generate a cosine signal, okay, of 2 pi delta f t. Okay, now let us do the following. يعني 100, it will be cosine 2 pi delta ft. If it is 010, it will be cosine 2 pi 2 delta ft. 110, it will be cosine 2 pi 3 delta ft. Up to what? Up to 3 ones, which will be cosine 2 pi 7 delta f t. Oh. So the second multiplier frequency will be what? Will be cosine 2 pi, say n delta f t. N delta f t. Of course, n depends upon what? Upon the code generated by the fh code. Now, if the fh code is 1, we have delta f. 2 delta f. 3 delta f, and so on. Now, so here at this point, let us explain it. M of t cosine omega ct will be multiplied by cosine, not omega, cosine 2 pi, say n delta f t. Well, now we have a new omega. Now look, please, go to the what? Go to the identity of cosine A, cosine B formula. It will be 1 over 2 cosine A plus B and plus cosine A minus B. Okay, so what we have at that time, the output of this one, and after filtering, based on the code, the carrier frequency becomes, signal becomes m of t cosine omega c plus what? Plus 2 pi n delta f t. Okay, this will be the output signal. So the carrier signal will be shifted by what? By delta f. Delta f means what? The channel bandwidth. This is implemented by what? By the frequency hopping code and the synthesizer. Well, do you have any questions, please? No. Frequency hopping, synthesizer. Okay, frequency code generator, FH code generator, synthesizer, and finally we have frequency hopping signal. Now, what about the receiver? Of course, you have to store the same code at the both sides. I mean, at the receiving and transmitting end, we have to have the same code. First of all, we have bandpass filter multiplied by the frequency synthesizer in order to down the frequency of the incoming signal, and using bandpass filter, and then we have binary phase shift keying demodulator in order to what? In order to recover the original signal. Now you can see in these two systems that the spreading system in the direct sequence separated spectrum system is performed in the time domain. In frequency hopping separated spectrum system, the spreading is performed where? In the frequency domain. We have good privacy and high security using these two systems. But if you are looking for higher security and better, say, security for our information, at that time we are going to make a mixing between the direct sequence separate spectrum and the frequency hopping separate spectrum. Look, please keep in your mind this important point. Now, in order to recover or reconstruct the direct sequence separate spectrum system, you need only one code, which is the C of T. Good. In order to recover the signal in the frequency hopping separate spectrum system, all you need is what? Frequency FH code. Okay, FH code. First one C of T, and the second one you need what? You need FH code. Now, if you are going to make a mixing between these two systems at that time, in order to recover any message, you have to have what? You have to have two codes, C of T and FH code. So the hybrid system will provide more security, but what? The system again becomes more complex as compared with direct sequence separate spectrum or frequency hopping separate spectrum. Now let's look at the transmitter and receiver of these two systems. At the beginning, we are going to what? We are going to perform the direct sequence separate spectrum. Look, data multiplied by C of t. Now this is spreading the data where in the time domain. Then we are going to multiply it by a cosine signal. So up to this point, we are what? We are performing the direct sequence separate spectrum, no more, no less. Now, in the second part of this system, look, we have FH code generator, frequency synthesizer, then we have cosine omega edge t or delta f, okay, the same meaning. Now, multiplying cosine omega ct by cosine omega ht, this will lead to what? To shift the carrier frequency becomes omega c plus omega h. And omega h value depends upon the code generated in the system. Then band pass filter, and the transmitted signal becomes what? Becomes ready. This is the what? This is the mixing or the hybrid direct sequence frequency hopping separate spectrum system. Now, for the receiver, first of all, we have to what? We have to down convert. I mean, the receiver of the frequency hopping will be used at the beginning. Then the deseparating using the C of T code, cosine omega CT for down frequency converter, band pass filter, and demodulator. Okay, this will be what? This will be the receiver of the hybrid system. Up to now, do you have any questions, please? Nina. Can you see the title processing gain or not?
بلا دكتور عندنا.
يا باشا. Alhamdulillah, we have a response. Good. Now, processing gain. Okay, processing gain. The most important parameter in the separate spectrum system is the what? Is the processing gain. Now, digital signal transmission is normally preceded by signal processing, such as filtering, modulation, and coding. Okay. At the receiver, processing like matched filtering and detection is used to recover the data. As you have seen in the different three systems that we have discussed, we have matched filter really. The effectiveness of the processor is measured with a factor called processing gain GP, defined as modified signal parameter at processor output over signal parameter at the input. Now, GP will be defined by two formulas. Based on what? Based on the kind of direct sequence, separate spectrum system. In direct sequence separate spectrum system, GP will be what? Will be RC over RB. And as you know, RC is greater than RB. So the processing gain always is greater than 1. Okay, don't be confused with the value of processing gain. We are saying it's a gain. Whether it's a gain, so the value of processing gain must be greater than 1. It's a gain, not attenuation. Well, so we said that the processing gain in the direct sequence separate spectrum system will be bandwidth of the symbol of the bandwidth of the bitrate, or it will be RC over RB, I mean the chip rate over the bitrate. And as you know, the chip rate is higher than the bitrate, so the gain is greater than 1. What will happen if you are talking about the frequency hopping? In a frequency hopping separate spectrum system, GP represents the number of channels. Okay, GP represents the number of available channels, N capital. Now, based on these definitions, well, we have an example. Look, example, a speech conversation. another example. I'm going to solve example 3 or 4, really. It's example number 4 in this lecture. A speech signal is transmitted using a direct sequence separate spectrum system. The speech is converted to PCM. PCM, it means what? It means the signal is passed through an A to D converter. PCM using an anti-aliasing filter with a cutoff frequency equals to 3.4 kilohertz. So the FC of the filter is 3.4 kilohertz. And using 256 quantization levels. Okay, now we have 256 quantization levels. It's anticipated that processing gain should not be less than of 23 dB. So minimum value for GP is 23 dB. Okay, look, GP sorry, processing gain alhamdulillah, equals to 23 dB. Now the requirement, find the required chip rate. Okay, find the required chip rate. So RC is missing. In branch B, if the speech was transmitted by an frequency hopping spread spectrum system, what would be the number of hopping channels? Okay, so in I mean branch A, RC is missing, and in the second branch, N capital is missing. Let's go to the whiteboard to solve such a problem. Now, you can see FC is 3.4 kilohertz, 256 quantization levels we have. GP is 23 dB, and RC and N capital are the missing parameters, and these parameters are required to be determined. Now, first of all, you have to what? You have to convert the processing gain into what? Into ratio. Okay, now GP in ratio equals to 10 raised to 2.3, and it will be 10 raised to 2.3. It will be 199.526. So we can approximate it to 200. Okay, say we have 200 in ratio. Okay, this will be the processing gain. Now, we said that the processing gain in the direct sequence separate spectrum system, GP equals to what? Equals to RC over RB. And RC is unknown. RB, of course, look at the problem. We have some information in this example will helps us to determine what? To determine the RB. First of all, we can determine what? We can determine the sampling frequency, which is 2 multiplied by 3.4, I mean 2F max. Look, the filter, low pass filter with cutoff frequency equals to 3.4 kilohertz. It means that the maximum frequency here will be what? Will be 3.4 kilo. So Fs will be 2 multiplied by 3.4 kilo, and it is 6.8 kilo samples per second. Now, Now we have another thing. Number of bits. We have to determine the number of bits which is used in this system. As you know, we have number of quantization levels, say 2 to power b equals to what? Equals to 256. Okay, 256. Of course, to determine b will be ln 256 over ln 2. Okay, and it will be it is 5.54517 divided by 0.693. So B will be B will be 8. Okay, now we have 8 bits. Good. Now, based on the information from the digital signal processing, RB will be what? Number of bits multiplied by what? By the sampling frequency. Okay, so it will be 8 multiplied by 6.8 K. And this will be 8 multiplied by 6.8 K, of course, and it will be, it is 54.4 kilo bit per second. Okay, bit per second. Okay, well, this will be the RB. Now easily we can determine the RC. Now GP equals to RC over RB, and GP is 200 equals to RC over 54.4 by 10 to power 3. RC will be 54.4 by 2. It is 108.8 multiplied by 10 to power 5 chips per second. Okay, this will be the unit of the RC. Okay, unit of RC. So we have high chip rate. It means 10.8 mega, 10 to power 6. This will be the bit rate. I mean, the first branch is obeyed and obtained. Now, what about the second branch? In the second branch, the question is talking about what? About, say, what will happen, our number of channels if the signal is transmitted using what? Using frequency hopping system. And as you know, in the frequency hopping system, GP is equal to what? Equal to N capital. So N capital will be what? Will be 200 channels. And this will be the last example in this lecture. Now, please, do you have any questions or not? Do you have any questions? Okay. If you don't have any questions now, I have finished the lecture of the separate spectrum. In the next week, inshallah, we have a lecture about the GSM. I'm rapidly talk about the GSM architecture, and we have another lecture about the separate spectrum, which will talks about the performing matched filtering. But I know by now we still have enough of time. Let us really go to that lecture. Really say, I mean lecture number 13. Still we have enough of time. share, yes. Yeah, start from beginning. Here we are making what? Making some review for this slide, okay, for the direct sequence and frequency hopping. And new information here, we have another system which is called time hop, separate spectrum signal. In this case, the transmission time is divided into intervals called the frames. Each frame is further divided into time slots. During each frame, one and only one time slot is modulated with a message, of course, based on what? Based on the code. Again, we have explained and talked about the Shannon law formula. This is again a review about it. Um, um, Here we are talking about the typical values of the processing gain between 10 and 60 dB. This will be a very simple example, really. You can solve this example. You can solve this example directly. And here we have a very important example. Look, in this example, we are going to what? We are going to transmit the three signals using what? Using the direct sequence separate spectrum system. And after that, we are going to recover the three signals. Look, in a direct sequence separate spectrum system, the information signal xi of t is multiplied by a wideband code ci of t, which is the output signal of the direct sequence ds generator. See figure below. The signal xi, ci, mi of t is modulated and transmitted. The signal occupies a bandwidth in the excess of the minimum bandwidth required to transmit information signal xi of t. Repetition period equal to the symbol period. Look, this will be the system for what? For performing the operation. Of course, modular 2 sum, it means we are going to use the exclusive NOR gate or exclusive OR gate to perform that. After that, at the final stage, we have to multiply our signal or the separated signal by what? By a carrier to be ready for the transmission using specific antennas and power amplifiers. Look at this baseband signal, please. Here we have a baseband signal, and this is what? This will be the PN sequence code. PN sequence code. Now, based on the PN sequence code, I mean the TC, we are going to multiply the signal by what? By the pin code in order to generate what? Xi of t by C of t. Please again look at the xi of t and ci of t. There is no 1 and 0 levels. We have 1 and -1 level. Why? Of course, to prepare the signal for what? For example, binary phase shift keying or binary frequency shift keying. Well, now, one, okay, look at this one within the period of TB. Okay, 1 by 1 will be 1. 1 by -1, again, it will be -1. Okay, then 1 by 1, it is 1, -1, and so on. Okay, so at the final stage, of course, slot by slot, you can to multiply the both signals to get what? To get the spreading code. We can observe from the above graph of our figure that the combined signal waveform has more high frequency changes in the data information since 1 over Tc, 1 over Tb, where Tb is the bit interval and is greater than the Tc information. Tc is called the chip interval. In the direct sequence separate spectrum system, the pulse shape is a sequence of short rectangular pulses called what? Called chips. Now, the chips are pseudo-random sequence of what? Ones and -1s. Okay, we don't have 1 and 0, we have 1 and -1, known at the receiver and often having repetition period equal to the symbol period. Example. This is the very important example. Now, consider signals transmitted from a base station to a mobile 1, 2, 3. The data streams x1 of t, x2 of t, and x3 of t are multiplied by what? By c1 of t, c2 of t, and c3 of t. Now, every user has its own code. Okay, we have 3 users, so we have what? We have 3 codes. Well, the resultant demodulated signal z of t, sum of m1 of t, m2 of t, m3 of t is given in figure below. Show that the transmitted signals to the mobiles 1, 2, and 3 are recovered at the mobile receiver by dissipating the resultant signal z of t, neglect propagation delay. Look, for the first mobile one, this will be the x1 of t, the message signal, c of t. Now directly, -1 multiplied by -1 becomes plus, okay? So slot by slot to get what? To get the m1 of t. Slot by slot multiplication to get m1 of t. Same thing for whom? For x of t. Now, again, here we have, look, -1 by 1 will be -1, okay? Slot by slot. And depend upon the TC. Why? The TC slot is smaller than the TB, okay? The TB time. TC time is less than the TB time. So the TC will be used as what? As a reference for the system. Now, M2 of t will be X2 of t multiplied by C2 of t. This will be M2 of t. Now, for the X3 of t, here we have X3 of t by C3 of t again, multiply the signals together, TC by the value of TB at TC. Okay, you can get the following signal M3 of t. You can try these values by your hand. Okay, now after that, the base station will transmit the 3 signals M1 of t, M2 of t, and M3 of t together at the same bandwidth. Look, after adding M1 plus M2 plus M3, this will be the resultant signal Z of t. Okay, this will be Z of t. Now, at the receiver number 1, look please, at receiver number 1, say mobile number 1. Mobile number 1 has code 1, C1 of t. So C1 of t is stored at base station and at the mobile, okay? Mobile unit and the base station unit have the same C of t. Good. Now here we are what? We are at the mobile side. Now, in the mobile, we are going to multiply Z of t by C of t to get this signal. Okay. Now, this is called dissipating signal. After what? After multiplying Z of t, I mean the received signal by what? By the chip code. Look, please, how we are going to determine what? To perform, I mean, the matched filtering. Please look. Now, this area, 1 unit, 2 unit, 3 unit, 4 unit, 5, 6, 7. As you can see, these areas, all of these areas are in negative. Look, 1, -1, -1, -1, -1, and this will be -3. Okay, so here, this area will be -7. Don't forget, within 1 bit, okay, this area is positive. So for the first interval, we have a value of -6. Okay, keep in your mind this value. You have what? You have -6. Now, in the second interval, we have the following: 1, 2, 3, 4, 5, 6. -2, we have 4. So here we have +4. The first one was -6. Here again, 1, 2, 3, 4, 5, 6, 7, 8, -2, it will be 6. Okay, so look here, -4, -6, 4, 6, -2, -12. Based on the 3 shoulder, negative values will be what? Will be considered as 1, and positive values will be 0. At the beginning, at the first lecture, we said I am going to consider or map the signal as follows. 0 will be 1 and 1 will be -1. Okay, so using the thresholder, negative values will be considered as what? As 1, and positive values will be considered as 0. So we can what? We can recover the original signal. Same thing for the mobile number 2. Again, we have Z of t at the input of the mobile multiplied by C of t, and this spreading, then you are going for determine the integration over one period of bit. I mean, add the areas under the curve, and again you will get positive and negative areas, and these will be approximated to 1 and I mean thresholded to 1 and 0 to recover the original signal. Same thing for the mobile number 3, and hence we can recover the whole signals. This is about what? About the frequency hopping and direct sequence separated spectrum. And we have discussed the last example, 3 mobiles connected to the base station, and for every mobile we have assigned, every mobile is assigned a code in order to what? In order to recover the original message or data. Next week, inshallah, we will continue with this lecture. We have in this lecture the use of frequency shift keying in the separate spectrum system, and we need about 20 minutes to explain the architecture of the GSM system and the block diagram of the GSM system. Now the lecture is finished. Please, if you have any questions, you can ask your questions, please.
بس دکتر
بله.
دمی ترم پیشنهاد چند لکچر داخل بند؟
سپرد سپکترم نداخله.
يعني حتى چند دن؟
خير داخلا، بس سبريد سبيكترم نداخله. يعني محاضرات افروي نداخله.
نقدر دكتور؟
والله بيا اسلجي من تسليم كان قسميه يعني ترى يعني ازنيشن بدل كم يعني اسلده في قسمي انوكا والله.
تمام دكتور.
اي والله عزيزي. ابا ماده من الترميه يعني وصناهيه ان شاء الله اسلجي بصناهيه نبزح متى يعني، بس اهم تشتت بخينه يعني درس بخينن وان شاء الله بصناهيه نبزح متى.
تمام دكتور.
لا يسار تشابه. Any questions please?
بس دكتور
بله عزيزي.
بهمور که تدانای موبایل به موبایل وقتی ما جزال شکرین هاگه ما تصحیح کربان جواب مثالی فرای کربا دم خان بابو مثل
نحو جيجا صنع هي أو موبايل تو موبايل. موبايل تو موبايل يعني starting point from a mobile, then the message is transferred to the base station. The base station they will passes the request to the MSC. Then MSC will passes the MIN to all base stations to determine what? To determine the location of the new mobile, and the rest of the diagram will be as connected, for example, to the landline telephone. Okay. قلب صنع هي نحو جاي حل لما تحلي قلب صنع هي. Any questions? Any other questions, please? If you don't have any questions, we have finished the lecture. Okay, now thank you and see you next week, inshallah.